believe it's a very healthy way to make connections between different areas, especially between math and statistics. We used to be so close. Actually, our department of statistics is from math. So anyway, let's start. So the title is Chatterjee's correlation coefficient. I think everybody, I don't think, but maybe some people know Chatterjee, who is a math and stat professor at Stanford. He did something, I believe, a big deal in random matrix theory, and he did a lot of interesting things in statistics, and this one is one of the most recent. So let's start the problem. Okay, I made a very ambitious goal. I wish everybody, I can walk everybody through my talk without like confusing parts, at least until the very end. So I will try that. So let's see what we can do. So the problem is very simple. It's one of the most classic problems in statistics. We have random vector x, we have random vector y. X is p-dimensional, y is q-dimensional. We wish to measure the dependence strength. I haven't defined it, but I hope everybody get a sense what is a dependence means. And the testing independence is about hypothesis testing of the non-hypothesis that is x is independent of y. Measuring dependence and testing independence are, of course, correlated. So it seems natural to put them together in one go. And we're statisticians. We're not going to do them without data. So the data we have is the cliche. We have NID copies of x and y. So I was a little bit struggled, like why is the random matrix part in my talk, but at least I can convince one this is a random matrix. So at least I'm still going to talk about something based on a random matrix. Here is our data matrix. So I'm going to use my data to measure the dependence strength as long as testing the independence. Okay. All right. That's everything starts from. So because this problem is super elementary, I set up some goals. Some of them are from a very famous mathematician and information theorist, Renyi. And he formulated in his, I think, 1955 paper in information theory. So he set up some goals for the dependence measure. First, this dependence measure, if we can call it mu xy, it should be between 0 and 1. All right, his goal. Second, it should be 0. Okay, so this one is a population measure. All right, it is based on only on the joint probability measure of x and y. It is 0 if and only if x and y are independent. All right, pretty nice. Secondly, this measure of dependence should be 1 if and only if x and y are perfectly dependent. What do we mean perfectly dependent? I will talk about it later, but you can imagine it should mean something about their sigma algebra. So they should be very close or even identical. All right, so again, it's slow, but I think I buy it. All right, so this is Renyi's criterion for defining a dependence measure in the population space. And I myself, I add 2 more. It is about estimation and testing, because we are statisticians, we are not pure math. We have to consider the data and making decision based on the data. So the additional criteria I would love to make is first, the estimator should be computationally fast, at least implementable, but hopefully fast. So in terms of fast, I think I hope to achieve near linear. So that means I can calculate this estimate of the populational dependence measure in some linear term up to some log n complexity. All right. So this is my first goal, and I think it is justifiable. We wish things to be fast calculated. And the last one, statisticians care about efficiency. So we wish our estimator to be efficient and ideally optimal in the statistical or information theory sense. in both testing and estimating perspectives. So our estimator should estimate the population measure efficiently, should be able to give a test of independence efficiently. All right, so this is my paradigm. And I will tell story based on these two slides. All right. So the outlines, I will give you some history, and believe me, there are tons of papers about it. I will just pick the best one, subjectively. And secondly, I will give you two brilliant breakthrough papers by Azadkia-Chatterjee and his students, now at ETH, Azadkia. And lastly is our contribution. So let's start with the simplest. That's the golden age of statistics, when we have the pleasure to only consider scalar random variables x and y, both one-dimensional, ID distributed. I assume they have continuous marginal CDFs for presentation simplicity. And again, our goal is measuring dependence and testing dependence. So now causal inference is a very hot area. So everybody now should probably heard things like association is not causality. So the simplest version of that statement is zero sample correlation or zero population Pearson correlation doesn't mean independence, right? Probability 101, you can create a bivariate T distribution will have Pearson correlation, population correlation exactly zero, but bivariate T will never be independence. So that means we cannot use something random matrix guys are familiar with, and I'm also familiar with the sample correlation or sample covariance matrix. It simply violates the criterion number 2. So the population Pearson correlation is not zero if and only if x and y are independent. So done. And something I personally like a lot, the rank correlation coefficients. I don't know how many of you know these two, the Kendall star and the Spielman's rho. They are very famous, well-used rank correlation measures of dependence. And like Zhidong Bao and his collaborators, they derived some Tracy-Widom laws and Pastor laws for the large Kendall star and Spielman's rho sample correlation matrix. But unfortunately, we still cannot use them for satisfying criterion 2 because, again, zero Pearson, Spielman or Kendall correlation doesn't mean independence. We can use the same bivariate T distribution as the counter example. So that means something we know how to apply the random matrix theory, we cannot study them. It simply violates the Reynolds criteria. So in history, what is the first one that gives us a satisfactory answer for dependence measure zero if and only if independence? It's by Vasily Hoeffding. So he gives a definition of the populational dependence measure in this very simple form. If you buy it, it is here the F, capital F is the bivariate CDF. F1 and F2 are the marginal CDFs, and he just measured we already call the phomesis distance between the populational bivariate CDF and the product of the marginal CDFs. All right, so this is his dependence measure. All right, and then you can prove that, and Hoeffding proved it 70 years ago. That is, first, this population measure of dependence is indeed between 0 and 1, trivially true. And secondly, and this condition is important, if the F is absolutely continuous with regard to the Lebesgue measure, then this populational dependence measure is 0 if and only if it is independent. And if F is not absolutely continuous, then we can find counterexamples, so that is true. But if we believe we can still buy absolute continuity, then it is indeed satisfying Reynolds' second criteria. All right, so Hoeffding's insight is not about defining this measure. I think everybody can define it. His brilliant idea comes with estimating it. So how to estimate Hoeffding's dependence measure, now called Hoeffding's D, is how U statistics was born. So let's go through. It's a simple algebra. We do this quadratic expansion, and the Lebesgue integration is linear operator, so this is trivially true. And you can prove it by yourself. The first term of this Lebesgue integration is actually just the exploitation of these two indicator functions, reminding that x1, x2, xn, y1, y2, yn are the copies of xy. Okay. Okay, you can verify it. And similarly, the second integral can be written down in this way. The third integral can be written down in this way. So once we are done with this part, how to estimate it is clear. It's a traditional trait of statisticians. We replace every population expectation by sample expectation. That is sample mean. And then in the end, what you have is an estimator of Hoeffding's populational D that is formulated in this form. Because if you look at, so here there are at the most, there are 5 tuples you have to consider for defining the, for rewriting the integration. So that means we have to consider 5 tuples and we sum over all such 5 tuples. And then this is, of course, a U statistic. That is a generalization to sample mean, because we are considering tuples sum instead of just the marginal sum. All right, and then this is the estimation estimator, and the next question Hoeffding asked is how to test independence based on this sample estimator. And he gives this interesting non-central limit theorem, and he shows that if x and y are independent, and of course having continuous marginal CDF, we got this weight convergence that is interesting. 70 years ago, it's very interesting. So by looking at it, we know it is not a standard central limit theorem because it is not weakly converging to a Gaussian distribution. It is actually converging to a convolution of weighted chi-square distributions, right? And nowadays we know this is a standard weight convergence result for something we call the degenerate U statistics. Degenerate means it is not converging to normal. And it means that actually this is not converging in root n rates, it is actually converging in n rates. And certainly, once based on this result, we know we can do a test, hypothesis testing. And this is one-sided because remembering the population D is always larger than, is always non-negative. And it is directly implementable. No permutation needed, anything not needed, because this is of a closed form, right? The right-hand side is a closed form and has nothing to do with the marginal CDFs of your data. This is intuitively right, because under independence, this statistics is just based on the marginal ranks of x and the marginal ranks of y, which are two permutationally invariant distributions. So it should not depend on the marginal CDFs. Okay, brilliant, right? Then let's review whether Hoeffding has answered Rennie's criterion that was posed about 7 years later than his paper. It should be between 0 and 1. We prove that. You prove that. You can. It should be 0 if and only if independence. Yes, as long as we buy absolute continuity, which should be okay. It should be computationally fast. I haven't mentioned that. So this is another part Hoeffding is brilliant. It's actually Hoeffding himself tells you, although that statistics seems to be involving summing over all the 4 tuples that will give us n to the power 4 computation, actually, it is not. It can be calculated explicitly in n log n time. Good. Statistical efficiency. He didn't mention that, but we can prove that. So it is indeed efficient. In terms of, so if we use the Clam's theory sense, so this is one way to say something to be efficient. It is for tests, its Pitman efficiency is larger than 0. So actually, we can show this is indeed true in the Hoeffding sense. So it is efficient. So the only one thing that breaks the whole story part is it doesn't have this one if and only perfect dependence one. That's of course, right? By just checking, reading the definition of this dependence measure. And actually, this one is not a really good measure of dependence in certain sense. All right. So we will talk about it. So it motivates some new research. And these are the two papers of ours that discuss some extensions about that one. And especially the first one is about random matrix. So not essential. So, so then Rennie reads this criterion. That means he must give us something. Right? He gave us some criterion. He should give us a measure of dependence satisfy this criterion. So what he proposes is this one. It is called the maximal correlation, literally, because it is maximizing the largest possible population Pearson correlation between all the measurable functions, transformations of x and y, as long as these measurable functions are indeed giving us a well-defined Pearson correlation. So then this one, indeed, based on his paper, it is between 0 and 1, trivially, because Pearson correlation is between 0 and 1. It is 0 if and only if it is independent. You can try to prove that. And lastly, it is 1 if and only if x and y are perfectly dependent. What is the notion of perfect dependence here? It is 1 so that the Cauchy-Schwarz will give us identity, right? So what is 1 that Cauchy-Schwarz gives us identity? Is that fx and gy, there exists some f and g so that fx and gy are equivalent up to some linear transformation, right? So this is what he gave us as a measure of dependence. But how to estimate it? You give us a population measure. To statisticians, it's just a beginning. But actually, it is very challenging. So unless your x and y are discrete, and actually you need it to be super discrete, right? It is nearly impossible. So then what he gave us is something that satisfies his criterion, but actually not satisfy our statisticians' criterion. And we just start here literally for about 60 years. It's a pretty big deal. So then here comes Azadkia-Chatterjee. So here is the setup for Azadkia-Chatterjee. So let me remind that Azadkia can deal with multidimensional x, but only scalar valued y. For some reason, we'll see later. And you may think about Rennie talked about this measure of dependence between y and x. This one is seemingly very good in terms of measuring dependence. It is also between 0 and 1 because of the law of total variance. And this one is indeed 1 if y is a measurable function of x, only if. But this one is actually not a very good dependence measure because it can be 0, but y is still dependent on x. Try to find one. It's the uniform distribution on the sphere. That one is violating the Rennie's second criterion. So then people developed this type of thinking until Dati-Sable and Stoiminov, I think they are Germans. So they defined in their 2013, not very long ago, this estimator. This population measure. It is close to Rennie's, but with a very important difference. So they are using the indicating function, not the original expectation. So this one, again, like Rennie's suggestion, it should be between 0 and 1 because of the law of total variance. It is independent. If they are independent, then class 0, simple math. It is if y is a measurable function of x, then class 1, again, simple mathematics. But the interesting part is the converse is also true. So actually, this measure of dependence is the one that also satisfies Rennie's criterion. That's a very good one. Then again, the problem is how to estimate it. Really give us someone that we cannot estimate. How about this one? So let me give you some notation. Ri is the rank of y. Ni is the index of the nearest neighbor of xi. Right? And here is Azadkia and Chatterjee's correlation coefficients. It's 4. Just read it. Super simple, right? And it is indeed an estimate of the population measure of dependence because they show it is almost surely strongly consistent estimate of Tsan. All right. Why is that true? First of all, I think it is really beautiful. And why it is true, we can just think about, so what is the expectation of Tsan? If the expectation of Tsan is close to Tsi, then it may make sense now. So to verify that, we can first check the equation inside the blue box. The important intuition is actually this one on the population Tsi is close to this one. Why? Because what is yn1? This random variable is really nearly identically distributed as y1 conditioning on x1 because of the smoothness in the space. These two are really like ID topics. And once you have that intuition, you check the denominator, you get this equation. It is approximately true. And then you can explicitly calculate this integration, you get the third line. And then this is because the empirical CDF is exactly the rank divided by n, right? Because you can replace every empirical population CDF by the rank divided by n. And then you got this minimum between the two ranks. So this is a high-level ideal. You can check his papers for more details. And then his one satisfied the first 4 criteria. So these are really good. So how about the last one? Actually, they don't know what is the limiting non-distribution, even if x and y are independent. That means we cannot even use it for testing independence unless permutation is used. And they give 2 conjectures. One is about the rate of convergence in the general probability measure of x and y. The second is under independence, the central limit theorem of their correlation coefficients. So this is our contribution. We settled down their conjectures and hopefully give you some idea about how to use that extended in the random matrix settings. Our contribution can be separated to 3 parts. Let's talk about first the limiting non-distribution. This is your second conjecture. The conjecture should follow a normal distribution. That is indeed true. So our main result is yes, under independence between y and x, and we'll assume x to be absolutely continuous. Just these conditions. Then we have the central limit theorem. And the QP is admitting this form. OP is admitting this form. And one important message is both parameters, QP and OP, are distribution free. Again, like the Hoeffding's D case, everything on the right-hand side is explicit under the null. All right. And how to prove it? Is by something we call the Hoeffding's representation. This is a tool Hoeffding developed 50 years ago. So we can show that Tsan, which has this rank part, rank is really subtle because rank is giving additional randomness to this statistic. And the goal is we replace ranks by the population CDF. And if we can replace the rank by the population CDF is a deterministic function. It has nothing to do with the data. That will make life much easier. And we can show that under independence, in the L2 sense, these two are nearly equal up to some small 1/√10 terms. And H is a function, deterministic function of explicit form. I will give you the form later. This is the Hyatt representation. And once this step is established, what you get is this statistic, this Fy statistic. And it is actually a nearest neighbor statistic. And the nearest neighbor graph is very famous for its universality property. It's not random matrix, but I believe very close. In particular, what we need is these two types of results about nearest neighbors. It is about the average number of edges that connected to each other. So the first one is about whether two nodes are the nearest neighbor of each other. So they are nearest neighbors to each other. And the second one is a very similar one. And the first one will be converging to QD. The second one will converging to OD. That is where the Q and O comes from. And with that, we can finish the job. Yeah. And then what about the limiting alternative distribution? This is the first conjecture. And actually, Sraf didn't ask for a limiting distribution because I don't think it is solvable. I will give you the evidence. He only asked about the rates, but we give them the limiting distribution. So our paper shows that as long as y is not a measurable function of x, that is the perfect dependence case. So as long as it is not true and both y and x are continuous, so x could not be absolutely continuous, just continuous. That means the CDF is a continuous function. Then you adopt weight convergence to normal. So this is so too actually when we share the result to Sraf, he shared a lot of excitement with us, and I visited Stanford on May, and we talked a lot about techniques. So this is a proof. So what is the challenging part about this proof is Hyatt's representation is very famous for being able to handle independent case, because under independence, the nearest neighbor, which is a function of x, it is the nearest neighbor graph of x, is independent of the ranks of y. That's very, very convenient. If we have independence between the ranks and the nearest neighbors of x, then essentially the calculation, we can minimize the calculation to maybe 2 pages. But if it is not true, if we don't have independence, then we need to track the dependence between the ranks and its nearest neighbors. So it will give us a very heterogeneous trajectory of y given x. So y given x will vary depending on how large x is. So the main result we got is actually we can show that this is always true, regardless of how dependent x and y are. And as long as they are not perfectly dependent, this is still true. And once this is done, we can use the similar techniques as in the nearest neighbor case to finish the job. So why we can prove that? We use a trick again. This one is a very general one. It is called Hyatt projection. It is actually the backbone of empirical processes theory. So the essential part of Azadkia-Chatterjee correlation coefficient is this one, right? We only have to study this one. And the essential idea of Hyatt projection is actually you give me whatever random variable you have. It should be in the high level approximately equivalent to this summation. And each one is a conditional expectation given only xk and yk. So that means this random variable inside the summation, they are IID. Right? And this is, in general, you have to prove it analytically. But here, in the high level, it is always here. And it will be very helpful for us to decide what is the hierarchy representation for the left-hand side. All right, so let's say what is this projected estimator. So the range, we decompose it to two parts. This may be a little bit technical. So essentially, here the conditioning xk and yk, it is inside this summation. So we have to separately consider the summation 1I is k and 1I is not k. And then we can formulate it to two parts. And I wish I can convince you that the first part is actually just this form, that is the hierarchy representation. We calculate the first component there. And the second part is it's just the second term, while HT is now explicitly found. All right. I apologize for being a little bit technical. You can check the paper. We give exactly the same formula. Yeah, it's not challenging. You just need to read it. So, but we do not have enough time. So let's move on. I still have 5 minutes. So as long as this step is done, as I promised, you only need one more result, again developed by Azadkia-Chatterjee. It's really magnificent. So his annals of probability paper, I think it is one of his most famous paper, really great paper. So we can use his techniques. It's essentially a version of Stan's method. We can show that this one, as a nearest neighbor statistic, will satisfy we can use Sraff's techniques to analyze this one, and then we can get in the end the central limit theory. And then the job is. All right. Then boosting efficiency. I haven't talked about efficiency. I just talked about the first two parts and how to implement the independence test. And actually, we get much more than independent test now. However, we have some papers, and Peter Beetle has some papers and some fabulous PhD students at Wharton and Columbia. So essentially, we independently discover the same thing. It's Chatterjee's correlation, although brilliant in many perspectives, is actually not an efficient, will not give us an efficient test of independence. That's how life is, right? So there is always no perfectness. So what is the reason why the statistically will not be efficient? It's simple. It's because it only consider the one nearest neighbor. And if you only use the one nearest neighbor of your data, think about the classic nearest neighbor-based density estimator or nearest neighbor regression. We know you cannot, if you just use one nearest neighbor, it will give us an inefficient estimator of the density and the regression function. So this is the main reason. And once we realize that we can give us some, we can boost the efficiency. For simplicity, let's just consider X here to be a scalar, one-dimensional. That will simplify the analysis too much. So we cannot resist the temptation to start with that. And let's NM, this time is the right nearest neighbor. So in a general multi-dimensional space, we cannot define right and left, but in the one-dimensional line, we can define it. So, and then we use this statistic. It will incorporate capital M many nearest neighbors, right nearest neighbors, to the statistic. And then we can show this one will be still a strongly consistent estimator. So it is actually not bad. You should consider using that. And as long as M is not scaling to infinity so fast, you get a central limit theorem. And notice this time is again a degenerate central limit theorem because root n times M is faster than root n. And then we got some explicit calculation of the expectation variance of cosine NM. And we have this picture. I have to explain it. but essentially, beta gamma is the detection boundary of our proposed statistic, and this on the x lab is how fast m will grow to infinity with n, and we can show that if m is growing to infinity nearly as n, so if gamma is close to 1, then we can reach the parametric detection boundary, that is 1/2 on the far top. And then you will have this is essentially like a bias variance trade-off. So when you're scaling up the number of nearest neighbors, the efficiency first increase and then decrease and then increase. So this is a typical bias variance trade-off. So then this one will have, arguably have the full criterion, but then calculation this time is not linear because m if is close to n, then this is quadratic but not a linear term. So we still need more research. So okay, so now this is the problems I wish you can give me the answer. I'm start here now. The first one is how to estimate the asymptotic variance consistently. So we give this one, we show the normalized version of Chatterjee is standardly normal. But for implementing like a confidence interval for Chatterjee, we need a consistent estimator of the variance of it. It's surprisingly hard. We don't know. Suraf gave us some idea, but they are I don't think quite ready. So I don't know. If you know the answer, I believe this will be a super cool thing to work out. And secondly, how to debias Chatterjee. Again, another thing I didn't talk too much. So it's bication Chatterjee as the dimension of x increasing is more and more biased value compared to Chatterjee itself. It will still be converging to, but it's not at 1/√10 rates or faster rates. So that means this part will have some trouble. To bootstrap work, so people love resampling methods for inference. But here, we don't know. So if you do the resampling and then you get the bootstrap distribution, does that distribution agree with this one? In short, it's not. We do the simulation, we know empirically it is not. But if we do some other bootstrap, m out of n bootstrap or whatever, can they work? This question. Generalization to higher dimension. So now here, the dimension is essentially very small, and generating to even high dimension, we don't know. So currently, we believe this will work very well if the dimension of x is smaller than 5, at most 10. But and lastly, you have Chatterjee correlation coefficients. You can replace the Pearson correlation coefficient with the Chatterjee correlation coefficients, and then instead of a sample correlation matrix, now you can have a sample Chatterjee correlation coefficient matrix. So what will be the random matrix theory part for this type of ones? So I think like some experts studied Kendall-Starr and Spillman's role. They got very fruitful results and published at top journals. So maybe this one will also give you a shot. These are the 3 papers so far we have, and I'm sorry I used 3 more minutes more. So and this is a brief survey. It's only 4 pages written by me in Bernoulli News. So if you wish to know some high-level ideas, you may probably see that. And that's it. Thank you.